Welcome to the second half of the semester in geography. You guys made it through weather and climate. I'm sure you did great. Now we get to geomorphology. This kind of stuff really excites me, and this is the reason I became a geographer. I started off wanting to be a geology major, and I'm taking geology, and the chemistry in it was killing me. I was a straight A student in college. My only grade that wasn't an A was a C in intro to chemistry that I struggled to get. I worked so hard just to get that. So to me, knowing that certain subject matter is difficult for some students, it just means you have to spend extra time on it. But I'm really happy that I got that C. That meant more to me. That hard C to get meant more than an easy A in a geography class that came really easy. But so geomorphology is different than geology. This was a co-requisite for me in the geology program. So it's a related field, but in a different discipline. And so I'm taking geomorphology. I'm like, oh, I like this better than geology. I wasn't really concerned about the chemical makeup of everything, including the interior of the earth. And it was more of the landforms and what things look like. So if you look at the name geomorphology, geo meaning earth, morphology meaning shape, this is what I like about being a geographer, is that we look at the landscape and see what caused it. Yes, there will be some chemistry involved, but not nearly to the extent there was in geology. And so my first course was an upper division course in geography that converted me to this love that I have for geography. So the second half, we're going to be looking at landforms and their distribution and how they vary over place and space. We'll break it into kind of two pieces. We'll have these tectonic and volcanic processes where we build things up, and then later we'll have weathering processes and landslides and rivers and glaciers that will shape it and erode things, transport things, and wear things down. So first we've got to have like the material that makes up the surface. We're going to get the volcanic processes that change it, the tectonic processes, plate tectonics, moving different directions, creating stress on the Earth's surface. So that's where we'll start. And then as we go through these last 8 weeks, we'll start to tear things down a little bit later. Now, for geography and physical geography, we're focusing at the Earth's surface. The Earth is huge. It's 3,500 kilometers deep or 2,200 miles deep to the center. I really am not that concerned about the interior of the Earth except for one outer layer that I'll talk about. I don't care if it's nickel, iron, copper, creamy nougat center. That's not an issue. Well, okay, I take it back. It's got metals in it, and those metals in the Earth interior generate our Earth's magnetic field, which is kind of important, but that's the only thing I'll ever say about the Earth's interior from this point on. What I'm trying to emphasize is that we're going to be dealing with this tiny little sliver at the outer surface of the Earth. We only barely go into the interior just for a little bit of movement that does affect the surface area. So to give you an idea, the distance to the center of the Earth, we're just concerned with this little thickness here. So the outer layer is referred to as the lithosphere. And the lithosphere has a crust upon it, but the lithosphere is hard rock material. It's solid. And yes, the technical word for the hard solid material is rock. The outer layer of the lithosphere has a thin crust on it, and there's a continental crust that has a different chemical makeup than the oceanic crust. So the oceanic floor has a thin crust on it, and then the continents have a crust on that as well. We will come back to this later because that subtle difference in the chemical makeup between the continental and oceanic crust comes into play later. Beneath the lithosphere is the asthenosphere, and this is as deep as we're going. I actually am looking at the slide to remember what the layer beneath the asthenosphere is. It's the mesosphere, and I couldn't care less. The reason we're concerned with the asthenosphere, and I put plastic in parentheses, is because it's a fluid. It's not like water, liquid, but it's a thick, viscous, hot, molten rock that's moving. And the lower areas of it are hotter, so you get convection currents of that hot asthenosphere molten material moving up, and then it cools and it comes back down. So these convection currents are moving the material in the asthenosphere around. But as they move, they're pushing against the lithosphere. And if we've got a convection current pushing in this direction and a convection current pushing in this direction, we're going to be stretching and putting pressure on the lithosphere, causing the lithosphere to move. So that's why we care about the asthenosphere, because the asthenosphere causes the lithosphere to move. And we'll come back to that when we talk about plate tectonics. So for a while now, we're going to focus on the lithosphere. And I said the lithosphere is made out of rocks. Rocks are the solid material at the surface and immediately beneath the surface. We have three types. We have igneous, sedimentary, and metamorphic. I'll go through all of these in detail, but the igneous, this is molten material that solidifies. Sedimentary is pieces of other rocks that gets carried somewhere, redeposited, and becomes a rock. And then metamorphic, where we take an existing rock and kind of change it through heat and pressure. So let me go through the three types, how we classify them, what we look for in the different rock types, because there's going to be different ways to classify them depending on the processes involved. So the first rock type are the igneous rocks. Now all rocks would have started as igneous rocks at some point because the earth was a big molten ball and it slowly cooled, and so we all started with molten material at the surface. So the molten material is referred to as magma or magma, but we'll stick with magma for now. Typically, if you're talking about magma, that's the molten material beneath the surface, and then lava would be referring to the material once it's on the surface, but it's a subtle difference. So when we classify igneous rocks, we're going to be looking at two different characteristics. I know I just gave a hint and then backed up from it. We're going to be looking at where it cooled, and we're going to be looking at its chemical makeup. So the where it cooled is, did it cool inside the earth? So that would be intrusive. So this is an intrusive pool of magma that cooled into an igneous rock. Or is it an extrusive rock where it erupted onto the surface and it cooled on the surface? The reason this becomes important is that igneous intrusive rocks, with that layer of material, it's called overburden, but with the layer of material above it, it pushes down on it, so it forms under pressure. It also insulates it, so it takes a while for that to cool and solidify. The opposite is true for the extrusive rocks. The extrusive rocks, they're on the surface, and the temperature of lava varies from roughly 2,000 to 3,000 degrees. But as it comes out onto the surface, it's significantly cooler on the surface, so it cools relatively quickly. There's nothing to cause it to slow down the cooling process. Also, it's not under pressure. If in many cases, it's the opposite, where the pressure is released and you may get gas bubbles inside of the rock itself because the pressure is released. Not unlike when you have a soda and you unscrew the top and all of a sudden magically the carbon dioxide bubbles show up in the soda. They were there, but they were held in suspension in the liquid because of the pressure inside the bottle. When the pressure was released, the gas bubbles came out. And so there are some rocks, like volcanic rock in particular, it's called scoria, where it's full of bubbles inside of it, and that's from the gases being released from the liquid magma when it cools without pressure on the surface. So our first way we look at it is, did it cool at the surface or inside? So the rocks I'm showing down here, the basalt, the gabbro, the rhyolite, the granite, these here, the lower ones, these would be the intrusive rocks. They cooled inside. Now I'll have better pictures in just a second. But because they cool slowly, they tend to be denser. And since they cool under pressure, they tend to be denser. And since they cool slowly, they tend to have mineral crystals that can develop. And they can separate themselves out and become slightly larger. Whereas the extrusive ones, they tend to be not quite as dense. They also don't really have lots of visible minerals without using a microscope or a hand lens to see them. So the minerals are significantly smaller because they cool so quickly. The minerals don't have a chance to fully develop. The other thing we look at for the igneous rocks is how much silica is in it. Now, we'll come back to this a little bit later, but there's a whole family of silicates, and they're silicon and oxygen that combines with other material to form a mineral. Well, silicates are slightly less dense. They're also lighter in color. They tend to, when you melt material and resort material to the Earth's surface, the silicates tend to concentrate in the continental crust and not in the oceanic crust. It's not to say you can't get them in one or the other. We just tend to concentrate those that are silicates, the felsic rocks, in the continents. In the oceanic material, we tend to get more of the basaltic, rocks, which are very low in silica. There are other material that are darker minerals that are common in the basaltic rocks. So your first clue that something is either high in silica or low in silica, is it light in color or dark in color? So these are high in silica, the felsic rocks that are shown over here, the rhyolite and the granite. Notice they're light in color. The low in silica, the basaltic rocks, mafic rocks, they are darker in color. It's easier to see with the basalt because some of the lighter minerals don't have a chance to really fully develop, so they're kind of in this matrix without the full crystals showing up. Again, like I said, I'm going to have better pictures of these rocks in just a second. So to reiterate what happens here with igneous rocks, we have two things we classify them on. One, did they cool inside or outside the Earth's surface? And two, are they low in silica, dark in color, or are they high in silica, light in color? So the extrusive rocks are formed right now many places on the Earth's surface. Hawaii's had an off and on eruption going on since the 1970s. Intrusive rocks, like you see here, the only way to see those is there has to be erosion and time take place to remove the overburden. So the low silica rocks, this basalt, this is an igneous extrusive rock. It's dark in color. This is something that would be formed at the Earth's surface. This is a Hawaiian lava flow from recent years. Notice you don't really see a good crystalline structure in here. If you had it under a microscope or even a hand lens with some types of basalt, you could see some crystals, but they're not really visible typically. So this is low silica, basaltic, extrusive, igneous rock. Very dark in color. Black, black, black. So the same mineral composition for an intrusive rock would be a gabbro. It doesn't show up well in photos, unfortunately. That's one of the limitations of doing this particular lecture online, where if I pass the rocks around in class, you guys can see the crystals. Now you just have to trust me that this is more sparkly than the other one, and you can see some crystals in it. So this gabbro has the similar chemical composition as the basalt. It's just since it formed in the inside, didn't get a chance to make it to the surface, the crystals developed. It's a very dense rock, and you have to have erosion to take place to expose the gabbro. There's gabbro in Yosemite National Park. There's gabbro in the Sierra Nevadas and some places within the Rockies. It's not an uncommon rock. I just happen to like the black Cullen picture because it's a very dramatic chunk of gabbro. Now, our extrusive rock here, instead of the low silica basalt, we've got the high silica rhyolite. And so the silicates make this light in color. So there's a lot of this in the Cascade Range. There's a lot of silicates in the volcanoes that are in the Cascade Range. It extends from Northern California up into southern Canada. So it's not surprising to see a lot of rhyolite in that area. Light in color, really don't get a good crystal development within it. This dome in the center of Mount St. Helens is a big rhyolite dome, the thick magma kind of cooling near the surface. As opposed to an igneous, intrusive, high silica rock such as granite, light in color, black and white speckles in it, mostly white, lots of quartz in this. Quartz is a silicate. And Half Dome is a big chunk of granite. There's lots of granite in the Sierra Nevadas, and you get really good development of granite in that area. We could do an entire class in Yosemite based on different things. Later we'll talk about Half Dome and why it's a dome, and then we'll talk about why it's a half of a dome as well. Just some different ones. Here you can see some of the air bubbles and what's going on. This cools super quickly, gets this glassy structure. Even with granite, you may mix a couple other minerals in there like feldspar or others that have a pinkish color. So it's not always going to be black and white. I'm just trying to demonstrate to you that there might be some variations in the different types of rocks that you see. And again, diorite, I'm not going to test you on diorite, but if you look at diorite, you would look at it and go, well, there's like 50-50. It's half dark and half light. Is it high silica or low silica? That measurement is kind of just a spectrum. So diorite is between a granite and a granitic rock and a basaltic rock. So it's an intermediate stage. So when you look at the rocks, anything I'm showing you, I'm kind of giving you a cursory overview. This isn't a geology class. We could spend 3 years on learning the different rock types and the mineralogy for the different minerals that are in it. I just don't simply have the time to do that. So we're giving you this broad overview of the different rock types. And when I'm talking about the high silica and low silica, this will come back again when we talk about volcanoes. So the next rock type are sedimentary rocks. These are pieces of pre-existing rocks that have been weathered and broken down. So it gets carried somewhere else by wind, by water, by ice, and then it's redeposited. So as these mountains wear down, those sediments make their way into the bottom of either the ocean or this lake, and they build up over time, and they build up in layers. Because we'll often see different climate patterns shift over the millennium. Maybe you go through a dry period and you get some wind-blown sand creating sand dunes. Maybe for part of the year, or for a while, the climate changes to a very wet climate, so you get lots of clays and muds. So those will build up in layers over time. Those layers put pressure on the rock below, and over millions of years, it lithifies. L-I-T-H is reference to becoming a rock. So the lithification process is the rock making process. So just because you have a layer of mud at the bottom of the ocean doesn't mean it's a rock. But if you come back in a few million years, when there's more layers on top of it, it's been subjected to pressure, it may go from being a layer of mud to being a rock. But that process of going from a layer of mud to shale is the lithification process. So how do we sort these? This isn't really as much of the chemical compound and where they happened, like igneous rocks were. This is more of like particle size, or this is particle sizes, I'll go through those, or whether or not it was something that dissolved in water and then fell out, that precipitated out of the water. So I'll go through this briefly, and then I'll go through it again in a little bit. So conglomerate, these would be like gravel rocks that are all kind of cemented together. This would be something that you'd find in a stream bed where it's transporting it. It takes a high energy stream to move conglomerate. It doesn't take as much energy to move sand and clays. So sandstone, shale, and limestone are way more common than conglomerate as a rock type. So sand would be, any guesses? Or sandstone? Sandstone would be sand-sized particles. Siltstone slightly smaller, and then shale would be clay-sized particles, very fine. This is, if you typically think of mud just being very smooth, that's solidifies into shale. And then there are some limestones that have different pieces of rocks in them. Limestone's really complicated because there's a bunch of different ways to make limestone. Now, limestone and other rocks too may dissolve in the water. So salt, for example, if you have a glass of water and pour some salt in it and stir the water, the salt magically disappears in the water, right? No, we all know it dissolved in the water. But if you go back to that glass a little bit later, you're going to notice that there's salt at the bottom of the glass now. That's because the salt chemically precipitated out of the water. So calcium carbonate, that's what limestone is, can dissolve in water, and then if there's still water, that calcium carbonate, the limestone, will settle out and build up in layers over time. So here we can see the pieces of other rock in the conglomerate. And this is all cemented together. It's a mud matrix. So this would have been the stream carrying the material down. As the rocks banged into each other, they rounded off each other's edges, creating conglomerate. The sandstone, the sand-sized particles, here you can see these are the wind-blown layers. This is at Zion National Park, but the layers of sandstone that build up over time. It feels like sandpaper for sandstone. Shale, this is clay-sized particles. Limestone, this particular one, this gray limestone, is chemically precipitated limestone. You can see a little bit of the layers of the clay that's built up to form into this shale. Shale is going to have a smooth feel to it because it's such fine-grained material. Unfortunately, with limestone, you typically have to do other tests to determine that it's limestone, because this limestone looks and feels a lot like shale. And one of the ways you would differentiate these in the field would you would put hydrochloric acid on it, because limestone, the calcium carbonate, reacts to the acid and it gets all bubbly. It's called effervescence. It gets all bubbly where the shale wouldn't get all bubbly. Sometimes when you look at these rocks just kind of separate, not in their natural environment, it's kind of difficult to picture how they are. So if you were looking at layers of rock, you typically would see layers of limestone, sandstone, and shale. Sandstone's easy to figure out, conglomerate's easy to figure out, but if you weren't sure if it was shale or limestone on the fly, just a quick little drop of hydrochloric acid, which geologists actually carry with them, you'd be able to determine which one it is. Now, limestone is an interesting rock because there's so many different things that have calcium carbonate in it, that you've got shells, you've got coral reefs, there's some plankton that are made up of limestone, of calcium carbonate. So when those settle, you can create different types of limestone. And this is why they'll fall into both the clastic and the non-clastic categories, but all of them react to acid. So this is Grand Canyon, where you've got this nice layer cake layers, the strata of shale, limestone, sandstone all through here. And when we come back and we'll talk about desert landforms, what's called differential weathering, we'll see why the shale makes slopes and why the limestone and sandstone make these vertical cliffs. But this is a very common feature in the Colorado Plateau area. It extends from northern Arizona into Utah, of these layers of sandstone, limestone, and shale. Here you can see more strata, both in the Grand Canyon in the lower right, but even these other formations where you've got the layers of different rocks. If you happen to be down at the beach, there's lots of cliffs in South Orange County, and you can see the layers of rock in them because they still show those nice horizontal layers. I keep talking about limestone, sandstone, and shale because they are the most common rock types for sedimentary rocks. Most of the rocks you're going to encounter in and around Orange County are going to be one of these three. That's not to say there aren't other ones around. We have some volcanic rocks, some igneous and some metamorphic rocks in our local mountains. Most of the ones in the coastal areas are all limestone, sandstone, and shale. We don't have any volcanic rocks, igneous rocks, in our coastal areas. Now for metamorphic rocks, here we're going to take a pre-existing rock and we're going to subject it to heat and pressure. So maybe it's new molten material coming up from below is pushing against rocks and it's heating them up, and the weight of the material above is creating pressure. Maybe through plate tectonics we're pushing material together, creating pressure. Maybe the rock is being pushed deeper into the Earth's interior from the surface. That's going to create heat and pressure. There's lots of different ways to put heat and pressure on rock, and it's inconsistent from one area to another. So our greatest variety of rocks are within the metamorphic family, because maybe this particular rock has more heat than pressure, but the same parent material let me back up. So I've got a piece of granite, and in one area it's subjected to a lot of heat and not a lot of pressure. It may create a different metamorphic rock than a piece of granite that gets a lot of heat and a lot of pressure together. So we've got a 100 rock collection at Saddleback College. 2/3 of them are metamorphic rocks, because you can even metamorphose an existing metamorphic rock as well. So I'm going to have to hit some of the key elements of metamorphic rock, but again, it's a pre-existing rock that's been subjected to heat and or pressure. One of the things you may notice in metamorphic rocks is there often the minerals that are in them develop into what look like layers. They're not layers, it's just an alignment. So if I start with kind of a random assortment of minerals, other than magnetic minerals, within a rock, most of the minerals just kind of develop in their own space and will be in multiple directions. But if I put pressure on both sides, I'm going to get those random minerals to kind of realign themselves. And so as they realign themselves, that will create what are called foliated bands. So this foliation in the rock is telling you that this particular rock was subjected to pressure from its top and bottom. And it caused the minerals to partially melt and partially recrystallize and realign themselves. So when granite is metamorphosed, it becomes nice. Don't take it for granted. It isn't nice. I love the second half of the semester because you're going to get more jokes like that too, by the way. Limestone becomes marble. I'll go through these again. Shale becomes slate. Sandstone becomes quartzite. And of course, we all know that olivine becomes serpentinite or serpentine. There's two different ways to say it. So our parent rock, what we start with, this igneous, intrusive, high silica granite. We subject it to pressure, in this case for illustration purposes, we're going to apply pressure from the top and bottom. We'll get that partial realignment of the minerals, the foliation, and it becomes gneiss. Just to give you guys a heads up, my 11-year-old in our complex, she can recognize the gneiss because we've got these big boulders and they've got banding on it. And when she was a kid, she asked why there was these stripes in the rock. So I got to explain the metamorphic process to her. So I hope you guys can identify gneiss as well. So limestone becomes marble. Now, remember what I said about the many different ways to create limestone? Your same thing is going to be with marble. You're going to see a huge variety of marble types and colors and patterns with the marble. They share characteristics, though they're still susceptible to acid. So one of the things you have to be careful is if you have marble countertops is to avoid spilling acids on them, like wine is acidic, which it's a tragedy itself because you spilled the wine, but it may etch itself into the marble. You would never have a limestone countertop because it's too porous and it would absorb the water. But when you make it much denser for metamorphism, then you could have a marble countertop because of the density of it. Shale, mud, you're not going to use mud to roof your house because it'll absorb everything. But slate becomes impervious to water because it's such a dense, solid rock. And slate you could use for roofing. Shale you couldn't. So slate is metamorphic shale. And then, of course, serpentine. This is the California state rock. You guys didn't know we had a state rock, did you? It's a cool looking rock. And its weird things is there has to be olivine. And we had a period of tectonic activity on the west coast of North America that brought a lot of olivine from the asthenosphere to the surface. But our compression along the west coast gave us lots of pressure, but not a lot of heat because it wasn't happening deep. It was just the North America pushing against the Pacific plate. And also for serpentine to form, there has to be salt. Well, we were next to an ocean. So we had the right components here. We had pressure, not a lot of heat, lots of olivine, and salt present to form the California state rock of serpentine. It's a cool looking rock. It's I don't know why for this particular page for the state of California they have an ugly specimen because there's much nicer ones as well. Here you can see foliation on a very large scale. Just again, different types of metamorphic rock and what you could look for. Here in schist, I didn't talk about schist. The minerals, when they align themselves, they kind of get squished and flattened. And so schist, one of the characteristics of schist is that the minerals will flake off. Well, all of these together are part of what's referred to as the rock cycle. And read about the rock cycle in your textbook. It's going to help you understand how the rocks are related to each other. I'm not going to give you a rock cycle question, but if you want to understand the three types of rocks, you need to understand the rock cycle. That everything starts as molten, it solidifies into igneous, that can be remelted, or you can weather it to make sedimentary rock, or you could change it a little bit to become metamorphic rock. So they're all related to each other. And we're not adding or removing material through all of these processes. We're just kind of changing the composition and we're changing the makeup, the density, all sorts of things in the rock cycle. Well, how long does this take to happen? I keep talking about like changing the earth, moving rocks around, molten stuff coming to the surface. Well, prior to the 1700s, there really wasn't a good explanation for things because when I say we in Western thought, this would have been primarily European thought, was that the earth was relatively young. And it's based on the Bible, that there was a giant flood and everything came to the surface. And so if you had a big canyon, what would explain the canyon? Oh, there was a giant flood. So the thought was the earth was roughly 10,000 years old. It's not really until you get into the 1800s where that thought process changes. And really, the father of modern geology is James Hutton. He was a Scotsman in the late 1700s, where he would make observations about things he saw happening now and would see them in nature as well. So he had a pond on his estate. The pond had layers of clay that were building up in the bottom of it, and he saw that that was similar to the layers of shale that existed. So his thought was if it took hundreds of years for that clay to build up in the bottom of his pond, it must take tens of thousands of years or hundreds of thousands of years for that shale to build up in 100-foot layers. He would also look at volcanic activity in the area, how some lava would have flowed through something in the past and then it's eroded away and something's deposited on it. So he would look at the steps that things would have to take place in order to exist as they do. And he kind of changed the school of thought as far as geology. So, of course, when I'm in Scotland, what do? I go to see Hutton's grave. So the idea of uniformitarianism, that the present is the key to the past. If we see sand ripples in flowing water now, and we see a rock that has sand ripples in it, what must have been here at one time? Flowing water. And so this type of analogy would work on multiple levels. Well, the problem with this is we still don't have a time frame for it. And at the same time, what were dismissed as kind of flukes or being not real, these giant bones we would find in certain places, and then fossils of things that don't exist anymore, by this time people are starting to organize them. They're starting to notice patterns, that they find certain types of fossils together, they find them in a certain order. They were finding similar fossils on different places on the Earth's surface, and those similar fossils would be with other similar fossils. And it was consistent. You wouldn't find, what's a good one to use? The trilobites. You wouldn't find trilobites with dinosaurs in the fossil record. But wherever you saw layers of rock that happened to have them both, the trilobites were always underneath the dinosaurs, which, you may remember, the youngest rocks are on the bottom as the layers build up on top. So no matter where they were on our surface, they may not have all of these layers, but they were consistent as far as which layer was younger than the other layer and which layer would have certain types of fossils. You never find dinosaurs with men in the fossil record, for example. So this was consistent over a large area. It really wasn't until you started doing what's called radiometric dating, where you would look at the radioactive decay of material. And this was obviously a 20th century invention where they could start providing dates for these different fossils and these different date periods. And so if you were to look at trilobite fossils and using the original methodology of, what are they found next to, what layer are they found in, okay, it's always the oldest. And then you did radiometric dating, you'd always find out that all of those trilobites were relatively the same age, and that they were always older than everything else above them in the layers. So the two systems would basically verify each other in the process. So then with the radiometric dating, then we get an idea of the age of the Earth, 4.6 billion years. And most of that was pre-major life forms. There were some crude life forms for a few billion years, but for the most part, life doesn't show up until the last 600 million years or so of the Earth's history. So we got 4 billion years of what's called the Precambrian, which is without life. And if we're trying to get an idea of how long that is, because 4.6 billion is such a huge number, if we were to compress that into 1 year, we don't get primitive or complex life with shell or skeletons until middle of November. They're in time for Thanksgiving. We don't get dinosaurs disappearing until Christmas. We show up, of course, it's New Year's Eve. We evolve in the evening on the 31st, and then that 1 second before midnight, humans first set foot on the moon. I had an anthropology instructor who would human life did not show up until the last part of history. If we look at the dust on this desk, human life represents the history of the world. And he was kind of overly dramatic, and that's actually how he spoke too. Whoops, sorry about that. That was the Facebook page I was just posting on before class. Let's put it a different way. If we had a beer that was 4.6 billion years old, humans don't show up until the end. Now, I'm not saying this to make human life seem insignificant. That's not the point. The reality is what I'm trying to show is that the processes we talk about take a long time to occur. So we have to have a rich, long history of tectonic and geomorphic activity at the Earth's surface for us to see some of the things we see. The Appalachian Mountains were formed over 300 million years ago. So that's to to see the erosion that's taking place, why they're worn down so much, is we've had 300 million years for that to happen. So we just to put things in time scale perspective. All right, when we come back, we'll look at plate tectonics. Thanks for listening.